Okay.
Ma'am, please start the session.
Yeah. So what I will do is, I will go through each of the point that is there in the lectures. So I am using this book, as a reference to explain the topics. The screen is visible to all?
Yes,
Yes, ma'am.
Okay. Yeah. So in this week, we are starting this continuous
But-
random variable. Okay. So first we have seen just the basic idea of like how is this continuous random variable coming. So as we know that when your data set is too large, you cannot assign probabilities to each of the outcomes that you have there. So in that case, one good thing to do is like you can split your data into, you can put your data into intervals and you can use it ever, and then you can use a continuous random variable to find the probabilities.
Ma'am, it can also come out of picture like naturally now. It's just not.
Sorry?
Not necessarily. Hello?
Yeah, can you
Am I
repeat?
audible?
Yeah,
Yeah.
you're audible. You're audible.
Yeah. So I was saying, is it necessary that it is coming out of an assumption only, like we are assuming it to be continuous, right? That's what you're saying. The data set is
No.
too large, so we can
They,
assume it will be continuous, right?
no, we are not assuming it to be continuous. What we are doing is we are putting that data in, like we are putting those data into continuous, like into intervals, right? So you know that if you have a large data set and if you put into intervals generally lie on real line, and then you know any closed interval will have a lot of data point, and you say such kind of variable to be continuous, right? This you have seen in stats 1 part, right? So this.
Yeah, ma'am, I've now understood one thing only. Like I
Okay.
understand that random variable is arising out of an experiment, and it is continuous because it can take any value out of any
Yeah.
real value, right? That's
Yes,
why it is continuous. I'm not able to understand why the probability of a single value is equal to 0. That's an issue.
Yeah, even that part is a little yeah, you just have to assume that for a particular point the value is going to be 0. The proof part is like
That is
very
true. I
tricky.
didn't get
Yeah.
it. Why should it be
That is a
0? Right? I
continuous
understand the
random variable,
infinite
right?
points.
Speak one by one. I am not able, both of you are speaking together.
No, ma'am. That is a continuous random variable. Now you are studying discrete random variable, right? Both are different, right?
No, we are starting continuous random variable only.
Okay.
So, ma'am, I was saying I understand there are infinite points, but that cannot be the reason that a single value is equal to 0, because the
No,
sum of
that cannot
infinite
be the
series,
reason. Yeah.
sum of infinite series can also come out to be like 1, right? So that cannot be the reason. And for even discretes are like infinite. In the case of discrete random variable, it can also take infinite values. So what is exactly the reason that the probability of a single point is equal to 0? Because whole
And
idea is like whole theory, mathematical theory is built on these points. We will define probability density function, not probability mass function, right? Due to this reason only.
Yeah, due
Ma'am,
to this
can I
reason
add
only.
something?
Yeah, please, sir.
Because let's see, if we are calculating the probability, then in this continuous random variable, we used to take the integration. And when you take, let's suppose you want to calculate the probability on 5, and
No.
the range
Hello,
will
hello.
go.
Actually,
Why
you are
you are
just
taking
going into the wrong way.
integration?
You are going top to bottom.
Yes.
Like
Why
you're
you are
trying to
taking
build up the
integration?
theory.
Yes. Why you are taking integration? Because we are can't find exact value. That's why you are going to integration, right? He
Yes.
said that
That's
why.
yeah.
Yes, because I have also doubt in this question. Why singular is 0 for continuous random variable?
Integration cannot be the reason. It's the other way around.
Integration,
Yes,
Integration
yes.
comes into the picture.
Integration comes
integration is
because
not the
we can't
reason.
find. That's why.
Integration is just addition. It is a
Yes.
Yes.
piecewise addition. Integration is not more than that. That is the only summation.
During
Yeah,
the
like you're
lecture,
dividing your reason into intervals and then you're just summing it over the areas.
Ma'am, can I add something, ma'am?
Yeah, please add.
Actually, probability density means probability per unit length. So when we take exact 1 point, unit length will be 0. So probability will be 0, ma'am.
Why? What is
the
that?
probability of the constant function is 0.
If you will fix
Because
the length,
Professor said that some infinity number comes. So that's
in
what I didn't
in
understand.
stats one,
Okay, I will just
instructors.
add one point here. So, all right. So this is what has to be added.
Numbers,
Can you
there is
make
infinite
a
number.
point
Not
here?
all
Why
the
why
number
Why
there is infinite.
probability at a point equals 0. So this is the point we'll add in the textbook also. So this has not been added yet.
Yes, ma'am. Please, ma'am. It's a real confusion because
Yeah,
integration and
we'll
calculations all
add
we
in
can
the
do, but it's the
Yeah.
fundamental point, right?
Yes. Somebody was saying in something.
Ma'am, can you just like make some comment on this point?
Ma'am, maybe we can continue and on the go we can clarify the doubts.
Yes, please.
Okay.
It would be great, man.
All
May I
right.
please go?
Yeah.
Please explain and this.
Okay, so basically what we are doing here is like when you have lot of data, all these data are just, even though they are just discrete set, but these are so large that you cannot go and assign the probability to each of these values. So this is how we are bringing this continuous nature into the picture. So we are dividing, so whatever data we have, like in this case we have two different situations. So one, we have taken the meteorite data, and other we have taken a condition where you have a binomial distribution. So in the case of meteorite data, you see that there are so many meteorites that are entering the earth and the weights are varying. So if you sit and just write the weight of each of these meteorites, you know that they are discrete set, right? Even though, because we are able to still count, so they are discrete set. So but it is not possible to go and assign a probability to each of them. It becomes very difficult to do it. So what we are doing is we are just splitting our this weight into in different intervals, and we are finding probabilities from there. All right. So similarly, in the case of binomial distribution, when you have binomial NP distribution, in case when your n is very large, so that case also, like finding any probability is very difficult, right? So even in that case, we try even in that case we try to bring it to the kind of normal distribution here. So this is a basic idea just for the continuous random variable. So sir has also explained in the lecture how we are dividing our like weight data into different intervals. So one way to do it that professor had explained in the lecture is to take log 2 to the data. So once you do it, you see that your weight is from 0.01 to some 60 tons, right? So weight is from 0.01 to 60 tons. All right. So when you take log 2 to this data, you have you get some smaller interval, right? And now this smaller interval you are splitting into different size. Okay. And so whatever number of values falling inside each interval, that you are counting, and that's how you are trying to find your probability.
Ma'am, here we
And the
have
same
taken log base 2. So,
log of
yeah,
weight,
ma'am,
yeah.
can we take log base 5 or something like that? Will it be possible, or just if we have to take log base 2 always?
Okay, log weight, weight 5. Okay.
It depends on the range of the
Uh,
data. If the range is very large, then you have to take log.
okay.
If
So
the
one
range,
more input that we got here is okay. I'll just write it here. Can we take log base 5?
Well,
Instead
that
of,
will like more reduce length more, right? If you take higher
if you
base,
take a higher base,
the
yes, your
length will
length
reduce more.
will reduce more.
range will reduce.
Range will reduce more. Yeah, that is there.
So
So
it
when you
depends
do
upon the
log
data set.
5, so when you do
It's
log
the minimum
5,
that we have to do at least log base 2.
yeah, so that also it's a good point to add. So this also we can just start it here. Okay.
Yeah, ma'am, understood. Ma'am, continue.
Okay. Okay. Yeah. So in the book we'll add that part also. It's missing, right? So same thing we are doing for the binomial distribution, and we can see that instead of going and counting for each of the data point what is the probability, so we can just plot the PMF. One way to do it is we can plot the PMF, and from there we can come up with some different come up with some different model and then try to find the probability. So this is just other way to deal with it. So this was just like the basic idea of why we are going with the continuous model. Now we'll look at very many terminologies that we're going to use here. So I will just write down what all is going to come. So you're going to see continuous, then you're going to see CDF, PDF, then you're also going to see this part, um, like exponential distribution, then you have uniform distribution, and then you will see normal distribution,
Yeah, common distribution part.
common distribution part basically. Yes. So these are the three topics that you're going to see today in week 3. Okay. Sorry, week 4. Yeah. So first of all, what is CDF? So CDF you have also seen in stats 1, right? So how do we define the CDF? So CDF is nothing but a function, right? It is a function defined from any real number to 0, 1. So CDF is basically probability, right? CDF is nothing but a probability.
Yes, ma'am.
Yeah. So it is the CDF for a random variable that in the continuous case we're writing it as fx of x. This is how we are denoting it, and it is basically a function from real number to 0, 1. Okay. And how is it defined? It is defined as fx of x to be equal to probability that x is less than equal to x. So if x is a random variable, right? if x is a random variable, so how do you define the CDF? We define it to be probability that your random variable x takes the value less than equal to x. Okay, and these are the few properties that a CDF has. So one is fx of p minus fx of a. So this is nothing but probability x lies between b to n. Then second thing to check is fx should be a non-decreasing function. Basically, it should be increasing function that takes non-negative values. All right, and as x tend to minus infinity, your fx should go to 0. So let's say if I have a random variable x here and you have graph for fx of x. Okay, so so as your x will tend to minus infinity, your fx should go to 0. And as your x tend to plus infinity, your fx should go to 1. So these are the four properties that a CDF takes.
Ma'am, can I ask some question?
Yeah.
Your CDF is a function from real number to
0, 1.
0, 1.
Yeah.
Real number also contain irrational numbers. Is that
Yes,
correct?
yes.
So what the probability is means something like occurrence of an event. So irrational event, how can irrational be defined irrational event?
No. So see, your x can be an interval, right? Your x can be a number, x can be interval. Let's say
maybe I can comment on that.
Okay, yeah.
So you are right that probability is associated with an experiment. So consider an experiment you are picking a point on a real number line. So
Okay,
definitely
yes,
the point can be the value of random variable can be irrational. Length can be irrational.
Yes.
So in similar way, if you are looking at weight, irrational number is a number, right? So weight can be irrational.
Weight can be irrational.
Yeah, it's just a number. No, weight can be any number.
Weight cannot be irrational, I think. Weight must be irrational because you can quantify the risk.
Okay, so leave weight. At least length can be irrational, right?
Length can be irrational also. Under root 2 is the irrational number. Length
and
can
we can
be
plot
irrational.
it, right? And we can plot it, right? So
you can plot it, yeah.
You can plot it.
Length can be irrational, right? So there are experiments which can result in a random variable having irrational values.
Okay, but this is very difficult to grasp. Means something means event can be irrational. Yes, please go ahead, ma'am.
Ma'am, can I comment?
Okay.
On the basis of this CDF, what somebody was mentioning earlier, that the probability that a function takes one value is 0 in a continuous function. That we can prove with the help of CDF. Suppose the function at one value at one point let us suppose that it is taking some it's a continuous function, and at one particular point it is having some value. It is having a positive value, not a 0 value. Then we are talking about a continuous function. If we plot the CDF of this function, at that particular point there will be a jump in the CDF. At that particular point there will be a jump in the CDF. But we already said that this is a continuous function and it has to have a continuous CDF. When we say it is a continuous function and it's continuous CDF, there cannot be a jump in the CDF at any point. So that is how we can argue that at any particular point, so our assumption that the function has a value at that particular point is not 0 is not true. Because if we want a continuous function, then it cannot have a jump at any particular point.
Okay, means you are saying that this definition itself.
Yes.
This looks some reason. Means yes.
Yes, he's whatever he said that is correct. Yes.
Yeah. So this
I think that will be
this is a reasonable explanation, right?
Yeah.
Continuous function, no jump. Since there is a jump
yes,
at
no
the discrete point,
okay,
so
yes.
that should be region.
That's
right.
why.
Yes. It is
Yes,
it is inherent in the definition itself. Yes.
Yeah.
So probability at any particular point has to be 0. If it is not 0, then it cannot be continuous function.
Yeah. So
But we have taken like random variable to be
using the
continuous.
CDF
Why should
approach,
CDF be continuous?
CDF need not be continuous. CDF need not be continuous.
That's the point now. This cannot be the explanation. We have taken random variable to be continuous.
Yeah. So
and you are saying CDF is continuous. That can, you're jumping
CDF,
from one point.
CDF can be discontinuous. So when you look at, so we have just looked at right now this, what is the definition of CDF. So after this, we'll also look at how the CDF of a discrete random variable looks like. Then from there we are going to define the CDF for a continuous random variable. Okay.
Ma'am, for continuous random variable, can CDF be discontinuous?
CDF cannot be discontinuous. If you have a continuous random variable, then your CDF should be continuous. Okay. Yeah, CDF should be continuous if you have a continuous random.
That is the point I was making. It has to be continuous.
So using
if
the
it
CDF
is not
approach,
continuous,
using the CDF approach, what it told is that is a valid point to mention.
So at any point, if the random variable takes a value at any point, then at that particular point the CDF is not continuous; it is jumping. So that is what we can say, that this because it is jumping, it is not a. But we assume that it's a continuous function. So,
but actually, it is counterintuitive in some sense. I don't know. It is only for me or some other person also, because like probability is adding up. The value of CDF is increasing, but probability of every point is 0, and probability, and it is adding up to something, right? So, yeah, that's something that's really counterintuitive. You are saying that as the function approaches, as the value of x increasing, the value of CDF is increasing. For every point is contributing something to CDF, right? But still, every point has 0 probability.
Every point is not. Every range is contributing. Every range is contributing something.
And range is made up of points only, no?
Range is made up of points, but range is made up of infinite points, no? So we cannot count the number of points in a range. For any given range, the points are infinite.
That's the reason. Yeah, that's true. But infinity is also we had in like discrete random variables. And now in continuous, we also have infinity. So maybe the nature of infinity has changed in some way.
Yeah, so this can go on for long.
Ma'am, maybe you can just add a point.
We'll keep it
Can you first explain?
Add a point.
We'll keep it
like
for
discrete random variable can also be infinite, right? And continuous cannot.
Discrete random variable is what? So any random variable that takes discrete values, basically.
Yeah.
That is a discrete.
But it can take infinite values, right?
It can take infinite values, but they are countable.
Yeah, they are countable. And here we have non-countable infinity, right?
So when we say like
it means there
natural number is countable, that you know, right?
Yes.
Natural number is countable, but when we talk about a real some interval in the real line, this is uncountable.
Infinitely many points in this interval.
Because irrational are included here. That is why it is uncountable.
That is why it is uncountable.
That is why probability at the irrational point is not defined.
That cannot be the reason. The irrational point is not reason.
Sir has given an example of a metroid coming. There are certain weights, different weights associated with each metroid, and he has said that due to the different weights, it's a decimal points can come in weights. So at that time, it's difficult to count the probability. So in that case, the weight was divided into segments like less than 20, less than 5, less than, So in that way, that is why we are using this type of continuous distributive functions.
Okay, maybe we should move ahead, ma'am.
Yes,
but still, please, ma'am, please go through this. Let's maybe add these points somewhere.
Yeah. So whatever things that are not there in this, we are going to add it. Okay. Also, why this
Yes,
interval is uncountable? Did you see this in maths 2 course
ma'am.
for
I
any
have
institution?
yes, we have understood it. Diagonal argument is there, no?
Diagonal argument, right?
Yeah, I know that.
Okay. So, all right. So this was the definition for the CDF that we saw. Okay. And then what are the properties a CDF should satisfy? So first is fx of b minus fx of a. This part that should be equal to probability x lying between a to b. Fx should be increasing function as x tending to minus infinity. Fx should go to 0, and x tending to infinity. Fx should go to 1. Okay. Now we have different few examples. So first we are looking at the Bernoulli random variable. So first we are going to look at basically discrete case. So in the discrete case we are going to look at very simple example here. So first is Bernoulli, right? So you know a Bernoulli random variable takes two different values. So one is success, other is failure. So success with probability p and failure with probability 1 minus p, right? Uh, Now if you have to plot the CDF for this function, right? So how will you do it? So you have x, you have this fx of x, right? And you know your x takes just two value, one is 0 and other is 1. Okay. So what is fx of 0?
Is 1 minus p.
No, this is going to be probability using the CDF, probability x less than equal to 0. Since x is taking just two values 0 and 1, we'll say this is just um, probability x equal to 0, that is 1 minus p, right? So fx of 0, you are saying it is 1 minus p. Let's say I'm writing this as 1 minus p.
Yes.
Okay. Sorry, this is
So x less than 0.
yeah, I got it. Yeah. So for x less than equal to 0, you know this is going to be 0, right? For x equal to 0, it is 1 minus p. So there is a jump here. It is 1 minus p. Now for x equal to 1, fx of 1 if we write, it is going to be what? Probability x less than equal to 1, right? And this is what? Probability x equals 0 plus probability x equal to 1.
That is equal to
So that
p
is
plus
equal to 1. So at x equal to 1, you have 1, right? So you see, as x less than 0, fx is, so as x tending to minus infinity, fx is going to 0. As x tending to infinity, fx is going to 1, right? So this is the plot for a Bernoulli random variable, the CDF plot for Bernoulli random variable. So this is the figure that you have.
I think we have not written it right.
Okay.
Because this one fx0 is 1 minus p only, because the first part is where x is less than 0.
Fx of 0 is 1 minus p only. See, there is a jump here, right? You see, this is added.
Fx of 0 is 1 minus p, right?
Yeah, fx of 0 is 1 minus p.
Okay. But fx where x is less than 0 is 0, right?
Yeah, right. So you see that there is a circle here. It means at x equal to 0, it is 1 minus p. See, there.
Okay.
All this. Yeah, let's take care of this. Now you have example of throwing a die, right? So you have a random variable x that denotes the outcome that you get when you throw a fair die. So you know when you throw a fair die, you have a distribution like this. So each of 1, 2, 3, 4, 5, 6 are going to take the probability 1 by 6 each, right? Now if you have to plot the CDF for this, okay? So let's say this is your x and this is your fx of x. Okay, so your x is taking the value 1, 2, 3, 4, 5 and 6, and fx should lie between 0 to 1. Okay, now let's see what is fx. So first case is when x is less than 0. You know, there is no such x which is taking the value less than 0. So fx of x will be 0, right?
0.
Even basically in place of x less than 0, you can do x less than 1. Correct? We can do it,
Yeah.
right?
Yeah.
Yeah. So in that case, your fx will become 0. So for x less than, I will use a smaller color. So for x less than 1, you are getting what? 0. Now for x, if x lies between, let's say for x lying between 1 to 2, okay, where 1 is included. Now in this case,
1 by 6.
your fx is what? Just 1 by 6. Right? So I'll just plot it here. 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6. So this is 1. So at x equal 1, you have 1 by 6. Then again you will have a jump. Then you have for x lying between 2 to 3, you will have 2 by 6. So you are just adding the probability taken by the previous value, right? Again here it is this. So you see this is step like structure.
Yes.
Yeah. Let's go to 1. So at each of the point you have a jump, and what is this jump length? This is just 1 by 6. 1 by 6. Each one is 1 by 6, right? So whenever you have a discrete random variable, if you have to find the probability for a particular value that a random variable take, you can just look at what is the length of this jump. So if you are able to find it, you can easily find the probability that this random variable takes. So from the CDF, this is one way to find the probability for a random variable taking a particular value. Now the next is some like general case where you have some x1, x2, x3, x4, x5, x5. These are the values that the random variable takes, and you have to and the probabilities with which take the value is p1, p2, p3, p4, p5, right? So how will we draw this graph?
First it will be 0, right?
Yeah, so you have some x1, x2, x3, x4, x5. Okay, so from 0 to 1, this is your fx of x. Now we are saying, so before x1, it is 0. Then x1 is p1. So you have some p1 probability. So this jump that you see here is p1. Okay. Then we are saying next, fx of x is p2. So basically, again you have, let's say here it is p2.
P1 plus P2.
Yeah. So this basically this distance is p2, right? This is what we mean.
Yes, yes.
Right. So again for x3 you have p3. Okay. So you have something like this. So this
Plus P2
distance is p3, right?
Yes.
Similarly, you have this as p4, and you have this as p5. So from here, if you have to find the CDF, so let's say you have to find fx of x1. What is this?
P1.
It is just P1. What is fx of x2?
It's P1 plus P2.
P1 plus P2. This is how you'll just have to add the probability with the previous one. So now you know, like given a CDF plot, you can find uh, the PMF, and given the PMF, you can also find the CDF. Okay. So next you have computing probability of intervals using CDF. All right. So next you have x taking the uniform value between 1 to 100. So x taking the uniform value between 1 to 100. So 1, 2, it's till 100. And you know the probabilities for each of them is going to be this 1 by 100 each, right? 1 by 100 and so on. So this is what is written here. So when
We're
you
still doing
find,
it for discrete, right?
yeah, we're still doing it for discrete. So if you have to find the CDF for, let's say, so again it is like what? At 1, this is going to be 0, right? So this is 0. Probability that x equal to 1 is what? It is 1 by 100. So I have 1 by 100 here. So this point here is 1 by 100, right? Then again for x equal to 2, you have 1 by 100. So you will go to 2 by 100, right? It is 2 by 100, correct? Are you able to understand this?
Yes, ma'am.
Yeah.
Yes.
So just you have to add everything, and similarly you will reach till 1. So at 100 you will have 1 basically. So you see you have many steps like structure here. We'll go on like this. So from there we are finding the CDF, or basically we are finding the probabilities. So probability, what is the probability that x is lying between 3 to 10? So you know, using the property of CDF, that you can write fx of b minus fx of a as probability that x lies between a to b. So this is what we will use. We will use the properties of CDF to compute the probabilities. From here we know how is the CDF defined, and we'll just using this properties to compute the CDF. Okay.
Ma'am, if like it is between 3 and 10, but 10 is not included, then the answer will change, right? It
Okay.
will not be same.
So you will have probability 3 x 10, right? So what you're
So
saying
we
is
have
this
to
is basically, yeah.
like fx. We have to calculate f(x) of 10 minus fx of 3, and then we have to subtract the probability of x equal to 10 also, right?
Oh wait, what you're saying? What should this be?
I'm saying fx of 10
Okay.
minus fx of 3
Okay.
minus probability that x equal to 10.
Probability that x equal to 10. Yeah, you'll have to subtract.
Yeah.
Yeah. Because here 10 is not included.
6 by 100.
Then it will be 6 by 100.
Hello, ma'am.
Yes.
Ma'am, can you please explain once again that which formula you are using now for calculating
Okay.
if it's 10
See
like
here.
10 by
Yeah.
100?
Just see here. So you have properties of CDF. You have when x lies between A to B, where B is included and A is not included. You have fx of B minus fx of A.
No, fx 10 is equal to 10 by 100. how you just calculate
Okay, that part. Um, look over here. You have fxk defined. So
Okay, k by 100. That means okay,
yes, okay, right?
okay, okay.
All right.
What if it had been x is greater than 3 but less than or equal to 9.5?
X is greater than. Okay, you're saying
It's
x
between
is
3 and 9.5.
9.5. Okay. So you're saying probability that um,
3, yeah.
basically this.
Yes.
So this you can write it as x less than equal to basically 9. X less than 9.5. So x is taking just discrete values, correct?
Right.
So 9.5 you cannot add. So less than 9.5 you can go till 9. So you will do fx of 9 minus fx of 3.
This is because we divided it in interval of 1. But if we divided it in interval of 2, then we will consider 8 for it.
Currently what we have, currently your x is taking 1, 2,
Yes, ma'am. Yes,
3,
ma'am. I'm
4,
talking about this.
so on till 100.
I'm asking, but if we take the values like 0, 2, 4, 6, 8, 10, then we will consider.
Okay, yeah. If that is the case, then you will have to do 8. Definitely, yes.
Question number B.
Sorry?
Question number B. 3.2 less than x less than equal to
Okay,
10.6.
see here. So using the property of CDF, what we did is we did fx of 10.6 minus fx of 3.2, right? But 10.6, okay, you write fx of 10.6. So using the definition of CDF, this is going to be probability that x is less than equal to 10.6, but you know that x is taking discrete value, so x cannot be 10.6, so you will have to stop at 10. So basically this is fx of 10. And how is fx of 10 defined? It is 10 by 100, right? Same
We
goes
can
for
say
fx
fx of
of
10.6 also, na ma'am. It won't matter to us,
Yeah,
right?
that is what I've written. I've written fx of 10.6. So why I'm writing this as fx of 10 is because it is a discrete. It is
It is just going to be
just taking
same,
a discrete value. Yeah.
Then which one we should take? The less value or money? If it is 10.6, we take 10. If it is
No.
like 9.
Why? See, just understand the definition of CDF. So CDF is what? CDF is defined as it takes any real value to 0, 1, right? And the question was, what is the probability that x lies between 3.2 to 10.6? Okay. So using the definition, using the property, what you wrote is this is same as fx of 10.6 minus fx of 3.2. Okay.
Yes.
Now fx of 10.6, uh, using the definition, what it is going to be? It
fx
is
of 10.
probability x less than equal to 10.6.
Yes.
So what you will do, you will add all the previous probabilities, right? You will add all the previous probabilities, but you can only go till 10 because you don't have 10x taking 10.6. So that is why this is equivalent of writing fx of 10.
Okay.
This is just the definition. Just go through it once again if you have any more confusion. Okay. So this was all about when x was taking discrete values. Now we are just going to approximate our CDF. So we saw how to plot CDF for discrete case. We are going to approximate that discrete CDF to the continuous case.
No, you are talking about the definition, no? This definition is in 1.2 chapter, right?
One, yeah, yes, right.
Okay, all these four properties.
Yes.
Okay.
So now what happens if you're like in this case you see that you had some 100 your random variable taking some 100 points, right? So similarly when your n becomes very large, so like in this case when n was 10 and you're plotting the cdf for a binomial n comma 0.6. So when you fix your n to be 10, in that case this is the plot that we got, the first plot. When your n becomes 20, this is the plot
Can you
you're
guys
getting.
please mute, ma'am? There's some disturbance.
Okay. uh, so when n is 20, so when your distribution is binomial 20 comma 0.6, then this is the kind of curve that you obtain for cdf. So as you see, as your n is increasing, your this discrete cdf kind of started looking like a continuous curve, right? Initially you had a step like
Ma'am,
structure,
I think the
you can
disturbance
see
is
the
from
jump.
your side actually. Ma'am,
Disturbance
I
is
think
from my side. Okay.
yeah, maybe you can readjust.
Is it fine now?
No, ma'am, I think some fan is like
Yeah, fine.
disturbance.
Oh, because of the fan you're facing a problem. Okay, just give me a minute.
We will manage. You continue.
Is it better now?
Yes, ma'am, it is gone. Thank you.
Okay.
Thanks.
Yeah. All right. So you see that now as you are increasing the value of n, as the value of n increasing, your the step-like structure that you were seeing for a smaller value of n, now it has started to look like a continuous curve. So this is like a continuous line here, a continuous line here. So as the value of n increases, your CDF, the plot for CDF that you had for discrete case has started to look like a continuous case. So from there, we will define our continuous random variable now. So what does the cumulative distribution function says? So any function f, okay, any function f that you take, which is defined from a real line to 0, 1, it is called a CDF when it satisfies these four properties. Okay, so these four properties we have already seen before for the cumulative distribution function. So here we are just defining that if you have any function, any function that you are defining from a real line, so you have a real line and you have a set 0 to 1. Okay, so any function that you are defining between these two, you will call this as a CDF when you have these four properties that your capital F function satisfies. So again, it's the same thing that we saw previously. So one is the function f should be an increasing function. Okay, then second is as extending to minus infinity, your f should goes to 0. As extending to infinity, your f should go to 1, and your f should be continuous from the right. So I'm not sure if you have studied this part in maths. So we're not going to deal with this part
Continuity we
here.
have understood, ma'am. Continuity we have understood.
Okay, so it should be continuous from the right, basically.
But why only from right, ma'am? Why should it?
Why only from the right? Okay, so this part also.
Because, ma'am, as second part, as x goes to infinity, f goes to 0.
Sorry, can you repeat? Okay, yeah.
In the second point, as x tends to minus infinity, f goes to 0. That's why f is continuous from the right.
Yeah,
I do not understand how is that a reason for continuity.
Actually, ma'am, this part technical if it's continuous, sir, in the lecture, sir has explained that it's a bit technical, which is quite tough. So this is out
Yeah,
of
I
our
remember
scope.
that it has been skipped in the lecture.
Yeah.
That part I remember. Yeah. But yeah, if you are interested in the explanation, we'll add it here. Okay,
It's just because I think it's just
yeah.
because
Okay.
it has turned to a continuous, but it's still a discrete function. Basically, we have reduced the scale. So the thing is that it's a stair function from the as we move from the right from the one greater than one to then we will be receiving the continuous part only. What I think.
No, it's no either it's continuous or discrete. There's no like, it's not.
CDF of discrete variable is not continuous, right? So even I
PDF,
am not.
you're saying
CDF of
PDF? Okay, CDF.
CDF of a discrete variable, random variable is not continuous. So even I was not able to understand this point. Sir has also not explained it in the lecture, but I was not able to understand this point. So if you could, I mean,
Yeah, okay. This part will add it over here.
Because a CDF of a discrete random variable is not continuous. You cannot say it is continuous.
No, CDF for a discrete random variable is not continuous.
Ma'am, but it's right continuous, ma'am.
It's right continuous. So if okay, if you take x from the right side,
Because when we have jump, that bold point will be included from the right side.
included from the right side. Yeah, that is there.
But even after it has become continuous, it's not continuous on the left.
No, we are just saying right continuous. We're not saying continuous. Continuous means it should be continuous from both sides, right? Both left continuous and right continuity, and it should give the same value. So if you look at this definition of CDF, you see that this discrete case it satisfies, right? You see it is a non-decreasing function. The second is valid, third is valid, and even 4 is continuous from the right.
Yes.
We can
So
check
this
these
is
3 points by seeing graph.
Fourth is not clear, ma'am. Fourth is not clear.
Fourth is not clear. Okay.
Fourth point is not clear.
Ma'am, the fourth point, it is valid even in case of discrete random variable, right?
No, it is
Even
not. In discrete, it is not continuous. For discrete, CDF is not continuous. So
no, from right side it is continuous. Right continuity. We have studied left continuity and right.
So I am not able to understand right continuity and left continuity.
So it means if you approach the value like from the right hand side and the value that it is taking at that point, that are equivalent. The same values. Right hand limit at that point and value at that point as well.
Whether you consider it from left or from right, the values will jump, right?
No. Here we are just talking about right side, not from the left side.
Okay, but if you talk about right side, the values are going to jump, right, from one point to another point.
No. Imagine.
So like you see a simple example here. Yeah. In this case, you can talk about.
So suppose let's say 6 at point 6. If as you go below 6,
if you go to 6 from the right hand side, right?
Okay.
You see, it is taking what? It is taking 1.
Right. As you go below 6, it suddenly drops to.
But we're not talking about that. We're not talking about
continuity. Continuity is defined at a point. So if we are talking about continuity at 6, you have to stick with 6. So you are saying right continuity. So right continuity implies that when you approach it from the right hand side, if you approach 6, so it is approaching towards value 1, right? And the value at that point is also 1. So it is right continuous.
Yeah. So whatever function you have, so in this case you have capital Fx, right? So this limit, when you approach this x from the right hand side, so you can write anything, is C plus basically, yeah. So in this case it is 6 plus, yeah, 6 plus. This should be equal to f of 6.
Okay, got it.
Right.
But left hand side it is not, right?
But if you look at from the left hand side, if you look at, this is not the case.
Yes.
So this is what we mean by the right continuity here. So if you look at the definition of the CDF that we have given, even that this satisfies the discrete CDF satisfies this all these four conditions. There is
Yes, yes.
some
Ma'am, but
music.
in
There's some music in the background. Can you mute? Yeah.
but
No,
fourth
I was
condition is,
asking
Hmm.
yeah, I
that
was
we
saying
can check
fourth
only
con
these 3 points by checking the graph.
Yeah, you can look at these three conditions by like checking the graph.
Okay.
Hmm.
See, if the fourth point is not so important at this point of time, can
Yeah,
we
at
move
this
ahead?
point of time, it is not so
Ah,
important. That
we
is,
will move,
yeah,
move.
yeah. Okay,
yeah. So, ma'am, I was just one bit, ma'am. I
okay,
was going to ask
okay.
for it is these all 4 points are valid for random or discrete random variables, right?
Even for
For
continuous random variable, it is valid, right?
yeah,
We will
for the
see. Yeah. Hello.
from left hand side also. That's what I am asking.
Yes, yes, yes.
It will be from both sides for
Yes,
continuous,
for
right?
continuous, you have it should be continuous from both the side. Limit
Yeah. Okay.
limit of
Okay.
fx as extending to c plus equal to limit of fx as c tending to c minus. This should be equal to fc.
Yes.
If this
See.
holds, we call it as a continuous, right?
Okay. Got it.
Yeah.
No.
Now here you have few examples given for the CDF. Now you look at all these graphs. So you see what is the first condition that you will check? Increasing function. Second is you will check as x tending to minus infinity, your fx should tend to 0. Third point you should check is as x tending to infinity, your fx should tend to 1.
One.
So if you look at the first graph, it holds, right?
Yes.
As x tending to minus infinity is going to 0, it is increasing, and x tending to plus 1, it is plus infinity is 1. Again, the second graph, the same thing is happening. As x tending to minus infinity is 0, it is increasing function, and as same thing is happening. It's the same thing here, also the same thing.
Yes.
So all these are so looking at the graph, you can say they are valid CDFs. So the fourth point, that is continuous from the right. So since these two are continuous, so it is valid. These are step functions. So, and looking at this, you can see that this is continuous from the right. So even the fourth point also holds.
Yes. But if the right hand side point is included, then this will fail, right?
Then this fails. Yeah.
What does it mean, large alphabet?
Okay, large alpha. So this graph that you see, so let's say this point, yeah, it's basically this graph. So when you have, let's say, a binomial random variable, the graph for a binomial random variable where n is, you have the parameter n and you have some probability p. Okay, so as you increase the value of n, you see how is the graph changing. So first, for n equal 10 you had this, for n equal 20 you had this, n equal 50 you had this, and n equal to 100 you got this, right? So basically, as you're increasing the value of n, how is this uh, discrete CDF, like this CDF started to look like? So this is what we are saying for large alphabet. So even though these points are discrete, but you have large alphabet, it means large value of n.
Okay.
Yeah, if you have large value of n, this is how the graph will look.
Okay.
Yeah.
Thank you. Actually, in this video, sir had mentioned large alphabet and he used the chi symbol.
He had used the chi symbol.
I don't know.
Okay, I don't
understand.
remember this part. Has anyone else seen that? You're saying he has written the
Yeah,
symbol?
I think that's what.
Okay, I will check this. Yeah, I don't remember him using this. Okay, I will see if it is there. I will add. Now you have probability of intervals using a continuous CDF. Okay. So the first example, not the first example, in between we had seen one example for a uniform distribution. Basically, yeah, this example. So you see that your random variable x, since it is a uniform distribution and it is taking discrete values from 1 to 100, still this value is very large, right? And for this CDF, you have this CDF and you see you will get some step-like structure, something of this sort, something of this sort, or like more closely you will get, right? Now what we'll do is we'll approximate this CDF, this discrete CDF, with a continuous one. So if you look at this graph, right, you can say that this is something as x by 100, right? So what we're doing is, since we had the CDF for a discrete random variable x, now we are approximating this discrete CDF with a continuous one. So this is how we have defined our continuous CDF. Okay. So once we define these two, we are going to check how are these values differing. So in the first case, we had probability x lying between 3 to 10. We wrote f10 minus f3, right, using this discrete CDF. So from there it was 10 by 100 minus 3 by 100, right? And even if you use the continuous CDF, the approximation one, you are getting the same value, that is 7 by 100. So in this case, you have not a major change. But when you look at this probability, x lying between 3.2 to 10.6. So using the definition, again, it is f 10.6 minus f 3.2. This is what you will get. And if you are using the continuous CDF, you will take this 10.6 by 100, right? But when it was discrete CDF, what we did is we neglected this part, right? In place of 10.6, we did it for 10 f10. So this is the difference that we are getting here. So in the discrete case, this was again 70 by 100, but here we got 7.4 by 100. So this is the difference that we are getting here.
Ma'am, I do not understand this. Can you please?
Okay, yeah. So what we're trying to say is, like,
understand that we are comparing to from continuous and discrete. You just can repeat it. Okay.
Yeah. So in the first case, we had seen for discrete CDF, right? And when you look at the discrete CDF, you saw there was a step-like structure, various jump were there, right? So when you look very closely, it is more like this graph, right? And how will you define this graph? You will define this as x by 100, right? For x lying between 0 to 100, it is x by 100, right? This is how you will define it. So what we are doing is, first we are calculating, previously we calculated using discrete CDF. And then now this approximated CDF, this is the approximated CDF, we are calling it continuous CDF. So we are calculating this probability using the continuous CDF, and we are looking at how much is the difference basically.
Okay.
So the first probability, you see, there is not much major difference. There is no difference basically. So even it was continuous or it was discrete, you still get 7 by 100. But when you look at the second example, right? So when you are using the discrete CDF, you got 70 by 100.
7 by 100, man. 7 by 100.
Okay, yeah, 7 by 100. Sorry. Yeah, 7 by 100. But now when you're using this approximated CDF, you are getting this 7.4 by 100. Right? So you see, even if you approximate it, right? Even if we if you approximate it, you don't have to really go and look for what all values your x is taking. You can just approximate it, and you can find the probabilities. The error you get is not a lot; it's very less.
Yes. So now I understand. Like, if we have a very large number of data points and they are within very small range, then the scope of this error will be very less, right?
Scope of error will be very less. Yeah. So you can
then we can
approximate
ignore
it. You can approximate it, and it will kind of give the same value for the probability.
So in this
That's
case,
the
it
reason,
was
sir.
Yeah.
in this case it was easy to find the
In
approximated
this case, it was
CDF.
easy to yeah.
But in certain curves, it may not be so easy. So,
Yeah, it is possible. Yeah.
sir has not mentioned the method to find the approximated CDF. He has given one example for that, but he has not given the method to find the approximated CDF.
There is okay. So one way. So how do you find this approximated CDF is first you'll have to plot this CDF for fx, and looking at the curve that you get for this discrete random variable for the CDF, from
No, I
there
think
you will have to decide what it can be.
There can be several approximations, right?
There can be several. Yeah, it is possible. But
the
which one is better?
Yeah. So in stat when we had like this point, na ma'am told us that we are going to learn this in like regression something we are going to learn.
Regression. So it's regression model you're not going to study in stats too, but definitely are going to study this in MLF.
Ma'am, so that is the reason, like if we have like same number of data points, but in like large range.
Same number of data point, but in the large range.
Yeah. So in smaller range, we want them to be in smaller range so that we have less chances or less scope of error, right? That's why we use algorithm function over there. Is that right?
Logarithm.
Yeah, logarithm.
Yeah,
function
log function. Yeah.
Yeah. We used it to like reduce our range, bring so many meteoroid data. It was in very large range.
It was in a very large range. Yeah. We want to reduce it to
small
range, smaller one. Yeah.
Yeah. So in smaller range, we have many data points. So
you have many data points.
Error, scope, the same number of data points, but within a smaller range. So the scope of error will be very less, right?
Scope of error will be very less, right?
So that's the reason we use that. Right?
Yeah.
Okay, good.
Okay. Then this is one more approximation that was done in the lecture. So again, how to get this start part is not done there. So how did we get this approximated CDF?
Method was not explained, but sir told that there can be better approximations than this one.
Better approximations are possible, yeah.
Yes. This was something about x minus the mean divided by standard deviation, something like that.
This part.
60 is the mean, and
60 is the mean, and 24 is the variance.
Variance. 24 is the variance.
Yeah.
It has something to do with that, but how he got this approximation was not explained.
Yeah, it was not explained. It is just one approximation for this like binomial is taken, and from there we can see it gives quite close values.
Sir was trying to tell the scope of the continuous random variable in this example. With this example, so how easy we can tackle these type of questions if we are using the continuous CDF.
Yeah, so this CDF is continuous, right? This affects. This is a continuous CDF.
Yes, ma'am.
Yeah. And this is a discrete CDF. So we have approximated this discrete CDF with this continuous one, and calculating fx using this is much more easier than going and calculating the fx for each of the values, right?
Yes, ma'am.
So it becomes easy to calculate the probabilities here, because you don't have to go and check for each of the values and add.
Yes, ma'am. It includes a very large number of combinatorics.
Yeah.
Yeah. Yes, ma'am. Yes, ma'am. Understood.
Yeah.
What is exp here?
Which part?
In the formula 1 plus exp.
Exp is exponential. Basically is 1 by 1 plus e to the power minus this part, Whatever is in bracket, right? You just write it here.
Minus, okay.
Yeah, exp is basically exponential. E.
Okay. How do we know it's negative?
This approximation is calculated using some way, and you got this approximation here.
No, but how do we know this is?
Oh, okay. Sorry, you're saying this is not negative. Sorry, this is not negative.
So if we find for
e to the power this,
we can find like in part A. We'll find F50 with this formula and also F40 with this formula.
Which formula?
This approximation formula.
Okay.
We will use to find in part A for 50, x is 50 and x is 40, right?
Yeah, right.
And whatever answer we get, just subtract.
Yeah.
Okay.
So, ma'am, in this formula, minus 1.65451x, is it given? No need to.
No, you don't have to. You don't have to remember this or anything. What is the idea here is, like, you had a binomial random variable with parameter n and p equals 0.6, right? And you have some CDF for this random variable x. This is just going to be 100 Cj 10. You know this binomial distribution, right? You're just going to keep adding. If you have to find for fx of 1, it is just going to be j varying from 0 to 1. If you have to find fx of 10, you'll have to add all the previous probabilities. If you have to find fx of 20, you will have to again add all the previous probability till from 1 to 20, right? So it is quite lengthy and it is very difficult to do it. It is kind of very difficult. So what we have come up with, an approximation of this CDF, of this discrete CDF, and this approximation is this fx equal 1 upon 1 plus e to the power minus 1.65451 into x minus 60 divided by under root 24. So this is one approximation that we have come for this discrete CDF. Okay. So
we learned that formula.
Yeah.
So we learned that formula approximation of this one.
No, we are not saying. What we are doing is we are just saying, since this is an approximated CDF, instead of finding probabilities using this discrete CDF, we can use this f of x to calculate the probabilities. Like, look at the first example.
That's why I'm asking this formula learned from finding.
Can you repeat?
Ma'am, what is this x minus 60?
X is a random variable and 60 is your mean here.
Expected value.
Yeah, 60 is your mean. So that is basically NP. This under root 24 is just under root of NP1 minus P.
Yes, ma'am.
So this is just one approximation that is given. So let's see, if you had to find this probability x lying between 40 to 50. So if you will use the first formula, right, what you will do, you will have to do F50 and then you'll have to add everything. 100 C50, it's very difficult. So we can directly use the second formula to find this probability, since it is just approximated CDF.
So, ma'am, in the examination, you given that one formula, or I learned that one?
You don't have to remember. You don't have to remember. That's what I'm saying. You don't have to remember. Any of it, you don't have to remember.
You given in the question.
No, there is no. Where is the question?
This type of question.
Even if we give this kind of questions, again the approximated CDF will be given to you.
Okay.
Yeah, so you can easily calculate. You don't have to remember.
Okay.
Okay.
Thank you.
All right. So now we'll move to this continuous random variable. So what do we say is, like, if you have any CDF, basically a valid CDF, then there will exist some random variable for which this happens. Basically, your probability x less than equal to x should be equal to fx. So if you have any, this is a theorem basically. So the theorem states that if you have any valid CDF, for that CDF you should there will exist a random variable x that will take values in R such that your fx is nothing but probability x less than equal to x. So this is a theorem. And again,
Is
what
there any like reason for it? Like some, I
any
can intuitively
reasons?
think, but still some rigorous proof, rigorous.
Rigorous proof.
Because this is from here we are like, this is where really continuous random variable is going to get defined, right?
Yeah, from here you're going to start the
Yeah. So this
continuous.
this is the fundamental. Here it will be
Yeah,
defined,
this is
and
the
I
fundamental.
think, and from here only that point will be clear that we are going to define it, na?
Yeah, from
So
here we are going to say that you have a continuous CDF. So you have, there should exist a random variable that is taking values in R such that
and
this
that would
happens.
imply that random variable having at every point value equal to 0. No, it's
Yeah,
not random variable having, sorry, the probability of
the
that value equal to
probability
0.
that your random variable takes a particular value is 0.
Here they
Because
have not mentioned that CDF is continuous. Here they have
no, it
just
is.
mentioned that given a CDF, there exists a random
Yeah,
variable.
given a CDF, you should I mean, if you have a valid CDF, it means there is a random variable for which this
That
happens.
But
CDF
if the
may be
CDF is
discontinuous.
continuous, then the random variable have to be like the value probability of random variable taking any value have to be 0 because it's
Yes, yes,
continuous as this,
yes,
because
yes,
it is not jumping, right?
yes, yes.
So that's what I'm saying. Here is what this point is really getting defined. So here I think a rigorous proof should be here.
Okay, so you want a proof for this theorem, is it?
Hello?
Yeah. Can
Yeah,
you hear me?
yeah, now I can.
Yeah. So I'm saying you want a proof for this theorem.
Yes,
Okay, so proof,
if it is
like,
not like part of the course, maybe you can point me
yeah,
somewhere.
I will point it somewhere. Yeah, sure, I will do. Not in this session, but definitely we'll see this. So all those points that I've noted down, that all gaps will update here. Okay.
Yes,
Yeah.
thank you.
Okay. So again, the CDF properties that we had seen before. So this is the first. Okay. Now you have okay.
So, ma'am, third property could not
Is
understand.
yeah, third property says is like if your CDF is continuous. So so what is this theorem saying? The theorem is saying that if you have a valid CDF, there exists a random variable that take values in R such that this happens, right? Now,
Okay.
if you have a random variable, I mean, if you have a valid CDF, so there should exist, and if the CDF fx is continuous, so the CDF is continuous, let's say the CDF is continuous, then what we are saying is there exists a random variable x that takes values in R such that this happens. So basically, your CDF, your random variable is also continuous. If your CDF is continuous, your random variable is continuous basically. And the probability that your random variable takes the value 0 at a particular point is 0 in that case.
Okay.
All right. So next we have a problem. So how will this graph looks like? How will this graph look like? So you have x here, right? You have fx here. Now when x is taking the value less than 0, it is 0. Okay.
Ma'am, it is not not the valid CDF.
It is not a valid CDF. Okay, let me check. So
X equal to 0, it is not different.
oh, I think this thing is missing here. Yeah, it should be.
No, ma'am, but during the lectures at the continuous CDF, we can avoid the equal to signs.
If it is continuous, we can avoid the equal to sign. But can somebody check what was there in the lecture?
We cannot, ma'am. How can?
But here it is
Like, but
less than equal to.
that it should be defined from R to 0, 1, right? So domain should be all real numbers.
Yeah, domain is all the real numbers. So for x less than 0, you are saying it is 0. Now for x, I think it is less than equal to. So for
That point is included.
Yeah. So at x equal to 0, it should be 0.5. It is 0.5. And again at 5, what is happening? It is going to 1. So at 5, it is going to 1.
Ma'am, here even if 0 and 5 are not included, suppose it is
Constant
not,
from 0 to 5.
it is less. If it is not less than or equal to, if it is simple less than, if it is simple less than, not less than or equal to, then also it is a CDF, right? It only means that 0 and 5 are not included in the values of the random variable. 0 and 5 are not included. Otherwise,
it is not about the value related to random variable. CDF always has the domain equal to real numbers.
Yes.
So only thing that 0 and 5 are not included in the domain. It's possible that.
No. Like if you even if you draw the CDF for a discrete random variable, there also you look at the whole domain is R. It's not like you're missing at some point the CDF is not defined. It is not like that.
It is mentioned above that it is that at particular point it is 0. Then how can we include that point?
No,
that
it
particular
is.
Point.
So it has to be defined for all real numbers.
Yes.
It has to be defined for all real numbers.
Yes, ma'am. Okay, then.
But if we say the random here, we are not saying anything. Has anywhere you saw that it's a random variable? I mean, it is a continuous random variable.
But for definition of CDF, they have not said that.
It's a misprint, ma'am. You are right.
Yeah, it's a misprint here.
Yes, ma'am. You have put the right mark on the red one. Should be the equal to sign.
Yeah, it is less than equal to sign.
Yes, ma'am. I have checked. It is in 45 slide number 45 of the PPT sections.
Yes, ma'am. If we don't include those points, then it cannot be rate continuity. We cannot talk about rate continuity.
Yeah, we'll have to add both the point. Yeah, actually that is a good point. From here, the right continuity does not hold. Yeah. So this graph will look something like this. The CDF. So you see that this CDF is like it's not continuous, right? The CDF is not continuous. Because you have a jump at 0.
Yes.
So such kind of distribution, you call it a mixed distribution. Now, what is happening? Okay. So first is what is probability x equal to 0? So you see, since at 0 there is a jump and this length is what? This is 0.5. So this probability will be just 0.5. Now what happens at, what is the probability that x lying between 1.99 to 2.01?
0.02.
So this is just, you will do f of 2.01 minus f of 1.99, right? and you can use this CDF. Similarly, probability 1.999. If you do this again, you can use this. Now the next is you have to find probability x equal 2 basically. So this 2.000. So you see the precision is infinite. It is not fixed. So in that case, the probability is 0.
And why?
Yes.
Because you're finding the probability for a particular point here.
Because at x equal to 2, there is no jump. We can say that.
Yeah, basically at x equal like 2.00000, like it keeps on going.
It's an irrational number. That's all we can say. No,
Not about irrational. I mean, you
what
don't
is
know.
this
I mean,
2.00? How
you don't know
it
at
cannot go
where
on
it is
forever.
going to stop. I mean, what is the precision here? So,
That-
like here, you see that it is 1.99999. At somewhere it is stopping, but this you don't
just
know where it is
because it
going
is
to.
not defined properly, that's why we can say that probability is 0.
We
Because
can
it is
have
not
infinite
defined well.
decimal expansion, and that's very properly defined.
Yeah, because it is not properly defined, then we can say it is 0.
No.
Even if it is x equal to 2 only, then it is also 0. Yes, ma'am.
Yeah, even if it is just x equal to, it is 0. Because at x equal to 2, the CDF is continuous. And if the CDF is continuous, probability that your x is taking a particular value is 0. This we saw in the properties. Like if fx is continuous at some point, then probability that x is taking the value.
Then probability that x is taking the value 5 is what?
Again, it is 0. Because it is continuous, right?
Okay.
Ma'am, my doubt is in I think in the fourth part.
The fourth part, yeah.
Yeah, x equal to 2.0000. What is this 2.0 bar? Doesn't make sense. 2.111 I understand. 2.121121 I understand. We have read infinitesimal expansion. What is 2.00? 2.0 bar doesn't make sense, ma'am. It is equal to 2
it
only.
is. I mean, it kind of like
any number after.
Somewhere it can stop. This is what it means. I mean, something, and it can, and then you can have some one. I mean,
I did not
basically,
understand
the
it, but-
precision is infinite.
Excuse me, ma'am.
Yeah.
Why is it at 5 is not, why is it continuous?
5 at 5 it is continuous, right? Look at this graph. It is a continuous graph, right? This graph is continuous.
It's not broken up.
Means, ma'am, how do we get that? Because that I did not understand.
This graph we got from this fx we have defined here.
So, ma'am, at 5, if you see, means if you can explain what happens at 0.5.
No,
Sorry?
part 5 is excluded. See, x is less than 5.
Differentiable.
At 0, it is 0.5.
Yeah, at 0, you see there is a jump. So probability that your x takes the value 0
And 0
is
I got.
0.5.
Yes, ma'am. Yes.
But you look at this graph here. This graph is continuous, right? So
It
same.
won't reach
So
5.
it means.
That's all.
So at x equal to 5, your graph is continuous. So looking at this property, so when your fx is continuous at a particular point, so here your fx is continuous at x equal 5, right? Then I can say that probability that x is taking a value 5 is 0.
Okay.
Could you please explain part 2 and 3 again? I'm just not getting all this.
Part 2 is what? Part 2 is you have to find probability 1.99 and 2.01. So using the property of CDF, the first point, this is going to be what? This is just going to be f of 2.01 minus f of 1.99.
Putting in the values in the second 1.5 plus 0.1x.
Yeah, you have to put this these value in this equation.
Okay, and likewise for part 3.
Yeah, likewise for part 3.
But in part 3, what value will I put?
Same value 1.99999, 2.0000001.
Okay.
Yeah. So when you solve it, right? When you solve it, you'll see this value will be much smaller. This third one, much smaller than the second one.
Okay. Why
So
so?
basically, as your interval is shrinking,
Yes.
your precision is increasing, your interval is shrinking, you are getting the value much closer to zero.
Okay.
You
Okay.
substitute
It
these
becomes
values here
like
in
a
the equation.
discrete value.
Not like a discrete value. You just substitute these values in this formula, fx.
Okay. And as far as this is concerned, say x is equal to 0, basically we're just saying if there's a jump, then it has a probability. That is, if it's discontinuous, right? If it's continuous, then it would have 0 probability. That's what
Yes.
the summary of this whole thing is.
Yeah.
Thank you.
Yeah. So basically, yeah, from there you can see that if fx jumps at a point, then it takes that value with non-zero probability, and if there is no jump, if it is smooth and continuous, then it takes the value with probability 0. So this is basically the summary for that problem.
Yes.
Now we have this continuous random variable. So what does it say? It says any random variable x with if we have a cdf fx of x, this will be continuous if your fx is continuous. If your fx is continuous at every x, then your random variable x is a continuous random variable. So what we had seen is, like, given if you have a valid cdf, then it defines.
Is there any reason for it? Like, why it should be continuous?
Sorry.
Can we define in precise terms why, if a CDF is continuous, it should be continuous?
Okay, what we had said is, like, if you have if you have a valid CDF, there exists a random variable x taking values in R such that this happens, right?
Yeah.
So,
but that X will be continuous if CDF is continuous. That's
so
what we are saying,
if you have a valid CDF, then you have some random variable x for which probability x less than equal to x equal fx of x. Okay.
Yes.
Now, now there is a random variable x with this CDF, and you will call this a random variable a continuous random variable if your CDF is continuous at every point.
What we are saying is that if CDF, the graph of CDF is continuous, right?
The graph,
So
looking at the graph of CDF of x, if the CDF is continuous, we are saying the random variable is continuous.
Yeah, so I'm asking then, like, besides reason why, if CDF is continuous, why should random variable be also continuous? We have a theorem that it should exist. There is a random variable x which should exist, right? We have said that for every CDF there exists a random variable.
Yeah, there exists a random variable.
But that random variable should be continuous if CDF is continuous. So
yeah, if the CDF is continuous,
can we give any precise reason for that?
Okay, looking at the graph, you can say that, right?
Because at any point, if it is not, because at any point,
I have intuitive reason for it, but vigorously, like analytically, I can even point out this is the reason, right?
Because at any point, if this CDF, because at any point, if it is, let's say that this effect, this random variable is not continuous, then at that point there will be a jump in the CDF, right? But we are talking about
jump will be if the probability is there, right? Jump will be probability is not 0.
Hello.
We are not talking about probability. We are talking about the range. We are talking about random variable itself. We are not talking about probability. These are two different things.
Hello, there is a theorem for that, but prof skipped the proof. It's like
Can you
beyond our
mention the
course.
theorem?
Maybe in next slide it's there, ma'am. In this course, in this only.
Okay.
Ma'am, I will check in the slide and I will tell you
Yeah, sure.
soon,
Yeah.
ma'am.
Okay, yeah, sure.
I understand that the probability equal to 0 from jump thing, but this thing, like, why it should be continuous?
Okay.
Ma'am, just to like for future references, like when we have like this practice book and all, and I understand that it is not possible to include each and every point, but for some things maybe you can point out, give some link or something where if someone is interested, the person can go and refer.
I understand. Yeah, I understand. Just fill in the gap. This gap also will fill.
Because some people, like we have done maths too and all, now some people are really interested in those points and some are not.
Yeah, we understand that. Yeah.
So but the persons who
fill in
are,
the details.
there should be some reference to.
Yeah.
Page number 37 in the slide, ma'am.
Wait, page number 37.
In the slide, he said.
In the slide, it says,
In the slide.
So, can you mention after what topic it's coming?
General random variable and continuous random variable.
Yeah, this is what we are talking about right now. Yeah, this theorem, right? This theorem only. This theorem only. Yeah, this we have discussed. This part, this part
theorem
we have
only
discussed.
We can say no, madam. If CDF is continuous, we will get continuous random variable.
Yeah, looking at the graph, it is clear. Looking at the graph, there is no issue.
I have intuitive definition, but why? How can you say, like, what are you looking in the graph? We can, like, can we precisely, like, point out? We are not able to do that. Like, we are just saying, like, vaguely, we are saying.
Yeah, if I come across some good explanation for this part, I will add it here, okay?
Let's move ahead, man.
Yeah. So in case of a continuous random variable, your CDF will not have any jump or steps. Probability will be 0 for each point, for each discrete point. And probability of x falling in an interval will be non-zero. And this will hold, basically.
Ma'am, last one was not continuous, ma'am.
Sorry?
Ma'am, the last example we saw was not continuous.
It was not continuous. Yeah. You see that at 0 you have a jump.
Yeah.
And this is 0.5.
That is why I was. Yeah, it has jump.
So these are the few properties that a continuous random variable holds for the CDF. So all right. So
could you just go to the third point, the last point? Explain this.
Yeah. Okay. So you have, let's say, you have an interval a to b. So basically, this you have already seen. Probability that x lying between a to b is fb minus fa. Now, what happens? Like, since x is a continuous random variable, probability that x will take the value a will be 0, and probability that x will take the value b will be 0. Right? So if I write probability x lying between, if I add both sides, okay, so this is going to be what? This is going to be fb minus and since see, probability that x equal a is going to be 0, I can, even if I just remove this, it won't matter, right?
Yes.
So I can write this as probability A less than X less than equal to B.
Okay, so it's the same.
Yeah, it's the same thing.
Okay. And likewise, if we remove the equal from the
other side,
less than or equal to B,
or from both sides, it doesn't matter, because at each point the probability is 0.
Okay. Yeah, I got it. Thank you.
Okay, so the first plot, this is a continuous. So these are the plot for CDF here. Okay. So looking at the first plot, this is a continuous CDF. So it is a continuous random variable. What about the second one?
Discrete.
It is a discrete random variable. The third one
looks discrete.
It is no, it is it is a kind of mixed distribution.
Okay.
We say. And the fourth one is again, it's a continuous CDF. So it's a continuous random variable. Again, you have another example done here. You can just check this one. I will skip this part. Okay. So all these problems, you can just solve it. So problem 2, problem 3. Just try it out, these problems. Okay, so now you have a probability density function. Since the probability that if you have a continuous random variable and you saw that at a particular point your probability is 0, right? So how will we measure the probability in this case? So that's why we are coming up with the terminology called PDF, that is called probability density function. So how is it defined is, like, if you have a random variable X that is continuous and you have a CDF fx of X, so the probability density function is defined as the like derivative of this CDF. So this we call it as a PDF.
When we are going to use it?
Sorry?
When we are going to use it?
So you can find basically the probability using both the CDF and PDF. So sometimes finding the probabilities using PDF approach is kind of a little easier. So to find the PDF, you'll have to integrate. You have to differentiate your CDF with respect to the random variable. So this is kind of useful when you're calculating the probabilities, or when you have to go from a PDF to CDF, CDF to PDF, all that. So exponential. Okay. We have a lot left. Sorry?
We have a lot left and it's almost been 10 o'clock.
Yeah, we have a lot left.
Can we take it in
sorry?
tomorrow's session? Can we take it in tomorrow's session so that we can also...
Tomorrow it's not possible.
6 o'clock, right?
Tomorrow there is no session. It's on Sunday.
Sunday session.
Sunday session we can do.
Sunday we can start from PDF if you want.
Yes, no problem.
Yeah.
So
I will inform. Yeah, whatever gaps you have told, I will refer to some material for that, and we'll also add in the book.
Ma'am, if like I told now, if there is like something which you think should not be covered or is out of the scope of the course, just give a reference to it. right? Where we
Yeah.
can go and add an extra document which is optional in some sense, right?
Yeah. Yeah. Okay. Yeah. That is noted.
Could I please request that in Sunday's session, when we start with PDF, we start completely afresh with PDF, not just
Yeah, I
property.
will start completely, yes, like
I
fresh
didn't
with PDF.
understand what PDF is.
Yeah, we'll start fresh with PDF.
Okay.
And also, like, I have a doubt, like, to the whole approach of it. Why are we moving from CDF to like defining PDF? Why we are just not taking, okay, there is a continuous random variable, and let's talk about it. Yeah, so there is this. Now, first we will define its CDF, then we'll move like going towards from CDF. We are going towards the random variable, right?
From CDF, we are going towards a random variable. They are saying it is a continuous. Yeah.
Yeah. So why are we taking this approach? Is it like the taking other way around will not be like sensible way to do it, or will it not be like logical, not a good way to build the theory?
So you're saying why are we not
That's why not start with, okay,
defining
there's a
continuous random variable and then we are defining a CDF, you're saying, right?
Yeah.
Yeah.
Why we are not taking that approach? Is there an issue with that? We build the theory other way around.
Yeah. Yeah.
Because we
We'll
have
look for
we know like what is random variable, we know what is a discrete random variable, and when we were talking about discrete random variable, we also said there will be going to be continuous random variables, right? So we can go in that direction also, but we're not taking that path.